Thank you. This is the first time I've actually stood up and used the mic. So here we go. Uh, Common Access Token, CAP for short. So what are signed URLs and tokens? Something that's used in video streaming. This is for content access. It's not necessarily for DRM. That's something different. So this is for how do you protect access to your content? Whether it's video, files, images, signed URLs are used in the industry different ways. The tokens can have different claims or criteria on who should access it or how they should access it. You can restrict it by IP address, geographic areas, time, whether you can access it before this time or after this time. And customers should be able to create these tokens for their users based on who they are, where they are, and what they want to do. So these tokens need to be created by the person who's creating the content for the people who are watching the videos. Some previous examples of how tokens or signed URLs have been used in the past. At Wowza Video, we patterned our token authentication or our signed URLs off of what Akamai previously did with their tokens, and they used a fairly simple way for doing it. They used a query string with a SHA-256 HMAC, which is just basically a way to sign the signature that's coming into the URL. So they use query parameters for this or cookies, and as I mentioned, it was pretty easy to implement at the time, but it was just one customer's way of doing signed URLs and tokens. A little bit of how that worked was you had a URL to like a playlist, an M3U8, with a query string that had the different claims or the criteria. This particular example has an IP address, an expire time, and the signature or what they call the HMAC, which is the signed part of the URL. So that would be used by the player when it makes an HTTP request for the manifest. How that sort of works on the edge or at the CDN, the client, they would recompute that hash based on a secret. So there would be a shared secret called secret there that both the person who created the token originally and the CDN knows, and they would use the SHA-256 HMAC with the string to validate have they actually tampered with? Did they change the IP address or expiration time? If that happens, those won't match. So if those match, the CDN goes into the next part where it actually validates the claims that are in the URL. So this particular one has an expire time, February 1st, 2025. That would check that it's still available to be played. And then it could check the IP address of where the request is coming from to make sure it matches what's coming in from the URL. So that was sort of an example of how Akamai implemented signed URLs at one point. Last fall, CTA 507 was published. So this was a standard that came out by SVTA for how to do these signed tokens. Instead of having everyone do it pretty much doing the same thing but in a different way, SVTA came out with a standard for doing these signed tokens. And the spec, I called an acronym soup. There's a lot of acronyms in the standard that you kind of have to wade through. You've got CAP, which is the Common Access Token. It is based on CBOR web tokens. I don't know if anyone's familiar with that. It's a sort of a binary representation of a JWT, which is a JSON web token. This is a CBOR web token. So what is CBOR? CBOR is a common binary object format. And this is also another standard, an RFC. I put the RFCs on there, but CBOR is a way of defining data, integers, strings, arrays, and buffers in a binary format, so it's compressed, so it's not as big. The signature for the CWT is CBOR object signing and encryption, which also has an RFC, which defines the way that you can actually sign these tokens, much the way JWT has. You can sign your tokens with that. CBOR has sort of a very similar method for defining and signing the tokens themselves. This was just a little size comparison that someone put together of a JWT with 3 different claims on what the token should be valid for. versus a binary representation using CBOR. And as you can see, it's quite a bit smaller when you convert it to binary versus using strings in the JWT. So a little bit about what the CAT standard is. As I mentioned, it's smaller size, it's binary, base 64 encoded, and one of the reasons that the size really does matter is CDN logs, right? If these things show up in your CDN logs for every HTTP request from every player, for every rendition, for every segment, you know, those will add up quickly in your CDN logs. So they opted for the binary representation to kind of decrease that size so that your CDN logs all of a sudden didn't become twice as big. And when you're talking about large events, that can be quite costly. They have a list of a whole lot of claims, same ones we had before in the Akamai examples: IP address, geo, start and end times, and they added a whole bunch of other ones too as well. They have a concept of having sort of multiple claims where you can have this and this or this, so they sort of are able to sort of stack the claims together and have some logic around them, which was kind of interesting. You know, if you wanted to support, you know, M3U8s or MPDs in part of your claim for the token, you could do that. Supports different signing methods. The same sort of shared secret SHA-256 HMAC, as well as private public keys to be able to sign it to if you want to be able to sign your tokens that way. That's also supported in the spec. Has some support for token renewal, probabilistic access, for, you know, being able to reject tokens that are coming in too frequently that should not. That's sort of the CDN leeching concept where someone will share a token, then all of a sudden you have a whole bunch of requests coming in from that token. These are still passed in as query parameters or headers or part of the URL for HLS streaming. They can also be used for dash streaming as well. Issues with query parameters in HLS. So one of the issues with using query parameters, it seems really easy at the beginning. I'm just going to put this in at the end of my URL and things will work. But those of us who have done HLS before know that when you get the playlist, you give the query string, it'll get validated, and what you get back is a manifest that says, here's a variant playlist, index 720 M3U8. It doesn't have the query parameters on it now, so that's going to fail because players will do that. You don't want to put the token inside the return value. You could if you did edge workers, but you don't want everyone getting the same token, so that was sort of an issue with that. Early on, players supported something called with credentials, which allowed cookies to be used by JavaScript players so that the CDN could actually set the cookie for that token so that subsequent requests could be used with that. Not all players supported it, so that was a little bit of an issue. One cool thing HLS did a couple years ago, HLS version 11, they added the option for query parameters. So that was a really neat feature they added to where you're able to actually define within the manifest query parameters and then use them later on in the manifest, so sort of do a replacement of that. That works really nice, but you have to have a new player, so players that built before or support HLS version 11 or less, like old TVs, old players, won't work. So going forward, that'll be nice, but it's just not quite there yet. One of the more common ways is to actually put it as part of the URL so that the token itself is included in every single request. That way, as long as the devices and the players are using relative playlists, the token just sort of persists as it goes down through all the renditions and segments and playlists. The other one that we did, which wasn't great, but we only protected the playlist for customers if they want. So it provides access to the top level manifest, but everything else is unprotected. That got support for old players, but honestly, it's not very secure. Anyone can just go and look and see the rest of it and download it if they wanted to. Let's see. The future of CAP. Hopefully CDNs will start to support this themselves. I haven't seen anything yet, but the idea would be that at the CDN level, they would support CAT tokens. This way, People don't have to actually implement the CAT spec themselves because really it's a CDN thing to do. If everyone's using the CAT standard, especially if you're using a multi-CDN sort of a player with multiple CDNs, the same token would actually work on both of them, which would be really nice to have. And the other thing too is this has a lot of support for the CDN leeching thing that I talked about, which is where this token can get copied from one person, leaked out and shared, and then people are using that token. This has support for that, like how many times you should see this token in a period of time and what to do, how to get people to go renew the token, different things like that is in there. I'll just take a pause there real quick. Anybody have questions? I kind of went kind of fast, kind of dry, but. All right, I'll take a little side thing. The one thing when I was going through the CAT stuff was they had support for geohashes, and I had not seen or heard of geohashes before, but I thought it was a really interesting kind of concept for defining geographic locations on the planet Earth itself. And what it is, it was published in 2008. It's sort of open sourced. It's not patent or anything like that. But it divides the world into 32 cells or grids, and each of those 32 have 32 more cells, and each of those cells have 32. So it just kind of keeps drilling down, down, down. In this example, the world on the left is the world map. 6 is predominantly South America. It looks like my numbers got messed up here, but you can see C is sort of the bottom corner of Uruguay, and then B up here is a little bit more of MonteVIDEO, and then if you wanted to drill down a little bit more, 1 would actually be down here in MonteVIDEO. So it's a very interesting way to get a location on the planet Earth. With that, you can do interesting things with it. If you get a geohash from someone of a location, if it's prefixed with 6D6F 696C, which would sort of be these 4 squares down here. These 4 here, they're mostly in Uruguay, right? You've got a few other countries in there, but it's a really quick way to sort of identify a location.
So can you use that and build that into one of your conditions for using CDN tokens for geography?
Yeah, CAT has geohash as one of its claims that it uses that it will recognize. The office at Qual Labs, that's the geohash address for the castle, I think, that's the one's the castle, is that right? All right. It could even, drill down even further if you want a little bit closer, so the palace would be 4 instead of 9. But we all have street addresses, right? Google Maps finds street addresses, so it's just not quite nearly convenient, but one example here I had is, if I'm down here on the beach, I have a really good spot, and I'm trying to tell my friends, hey, I'm halfway down the beach, I'm next to the person with the red umbrella, come find me. Those are hard directions to give. I could just give them that geohash, and that is actually, there is that little green box. That's where I've set up my camp for the afternoon on the beach. And they could come find me right away. So not really related to CAT tokens, but I just thought it was kind of an interesting way to do geographic locations with that. There is, if you go to, if I back up, geohash, if you go to that URL, it's a really neat little website. You just start clicking on squares and drill down, and you can find your house. You can find anything in the world, and it kind of gives you however resolution you have, you'll have an address with that. So that's it. Any questions about the common access token using concise binary object representation, object signing encryption, web tokens? Yes. Oh, good. A question. There are things on the internet that will take like a Latin long and convert it into a geohash itself. So you could sort of, if someone gives you a Latin long address, you can convert that. There's math on how to do it with what they have. But basically, this represents 6 on that world grid. And then anything inside of this square here is 6F, right? So, and then depending, that's where I said, if you want to be in Uruguay, you're in one of these 4 squares. It's not great because it does pick up some of Argentina and Brazil because they're bigger boxes and they don't just fit around countries nicely, but you can kind of generally tell where that is.
Recursively go deeper.
Yeah, you could definitely, you could take 6D and then whatever squares are in this one and 6F in here. So you could, depending on how far you want to go, you just have more and more options, but yeah. Cool. Anything else? All right, thank you.
Cool. So this is an opinionated tour of live captions. And my name's Scott Kellicker. I'm a video software developer. I have my own single-person consultancy. One fact about me is I have good hearing. So I do not rely on captions. However, that's not true for everyone. And so I love this. I love this from Silicon Valley. And if you're in the video industry and you've not seen Silicon Valley, it's kind of required viewing. So they have this meme about making the world a better place. And all these people are doing their pitches about making the world a better place through these ridiculous things that are really about making money. However, in this industry, we have a way to make the world a better place, and it's through live captioning. And I'm going to show you why that is and some things we can do to do that. We're going to start with an activity. The activity, I often watch live video content with no audio and the captions on. And that is to experience what other people experience. And I really would like you to try that. You will be surprised at what a poor experience it is. So find something you really like, the Super Bowl, the World Cup, whatever it might be, a talk show, a political talk show, and try to follow the content just with the captions. You will not believe what a bad experience it is. And we have made strides in that area already, but we are far from where we need to be. So the activity I have, this is a short activity to experience this. I have about a 1.5-minute video. It's a show called Morning Footy. It's a live talk show about football that's on in the United States. There are two cuts of this. You will not have audio, you only have the captions. So I want you to watch it. I want you to watch it for 2 things. The first is, what is your experience following the content? And the second is, look at the 2 videos. They're different players, so they have slightly different experiences. And I want you to decide which one is better for you, and then we will talk about what we find. So, yeah, go ahead. Thank you. This one will be a little different. Can we switch back, please? Thank you. So I bet you noticed quite a few things in there. If we had more time, I would actually ask for contributions. But some of the things I noticed were you cannot tell who's speaking. The captions obscure important content. There's caption latency, which you can't tell because you couldn't hear the audio, but it's typically 4 to 8 seconds. That's pretty normal, and that is okay. I found it too fast to read. And there are a lot of incorrect words, which, again, because you couldn't hear the audio, you may not have noticed. But this was in about a 20-second period. And I did not go looking very hard for this content that had incorrect words. This is very common. Wrong player name that doesn't exist instead of the word injury, a sentence that has completely different meaning. So this is what people were experiencing. And then you also notice that there were 2 different experiences. This is desktop, and this is iPad. This is centered. Each line is presented completely and then scrolled up. On the iPad, it's transparent, it's left justified, and the words build one at a time, and then they scroll up. Show of hands, who liked the first one better than the second one? Yeah. See, this is funny because in my family, it's 3 to 1. My wife likes this one the best. The 3 of us like the individual word building. So that's the majority opinion, yeah. So I'm going to back up and talk about some caption basics just so we have some common language. This is a really broad topic, and I'm going to go fast. First of all, hearing loss. 1.5 billion people have hearing loss, 20% of the population. And 430 million have disabling hearing loss. So when I hear people say we don't have money for accessibility, find me an audience that you can grow that big that's any other demographic. And that's not why we should be doing it anyways, but sometimes we need to make those arguments. Disabling hearing loss, this is US statistics, grows from 2% to 55% when you're 75 or older. So this is really, really important. Besides deaf and hard of hearing, there's lots of benefits of captions. Sound-sensitive locations like airports and bars, hard to understand audio, accents. We were talking about this at lunch today, different accents that we have trouble understanding in the same language. Often it's the listener's second language. Something I did not know until I was studying this is it's also a really good way to process information in a different way. So if you're neurodivergent, have ADHD, autism, captions are really important for you to help process. And it's also a really good way to learn something new, because it's another way of reinforcing the way the information comes in. So now we're growing the audience even more. Captions versus subtitles. And I wanted to replace this with the hat picture, but I ran out of time. But a caption is for if you cannot hear the audio. Okay, it's a transcription. So here's our live video, JP welcoming us to camp. This is what the caption looks like. It's in Spanish because that's his language. A subtitle is about language understanding, so it's a translation. So in this case, the subtitle is translated to English, so greetings from camp. So that's generally the difference. Live caption workflow, basically, you get live in, you pull out the audio, a human or AI or some combination of both transcribe that information or translate it, and then the captions go back into the stream and it goes to your player. Super simple. There's a few more things to it than that, but that's generally what is happening. AI and captions. AI is really important to captions. You'll see the acronym ASR, automatic speech recognition. This is basically AI that is doing the transcription and translation. So it's doing a really good job. What I hear again and again from everyone is it's just going to get better. I hate that term because it basically says we're just waiting for it to get better. There's work we need to do to make it better. We actually need to measure it to see if it's getting better. And I'll talk about that in a second. I'm going to skip measuring word accuracy. It's a really complicated topic. But there's a way to measure it's just like per words, and then to measure meaning, which is a little bit softer way of measuring. It's a little bit like PNSR and VMAF in our world. Like one's more scientific and one's more about perception. So let's look at some of the pain points that we saw. First, word accuracy. This is the most important one. You need to get the words right. I'm just going to make some suggestions. First of all, we need to measure it. We always need to measure it. I've transcribed several live broadcasts and kind of compared the captions. I found that if 2% or less errors, I can actually follow the captions. Typically, what I find is most broadcasts are 5 to 10%. So we're not there. There's also no real standard. Like we have certain measurements, but everybody's self-reporting. Everybody's using different tools to evaluate those things. So we need some type of standardization. So when company A says, yeah, our error rate's this, we know exactly what that means, and we can have a common language around it. And we also need to do more retrospective of the actual events. Like, how good were the captions? Like, humans have to sit down and translate that and compare what we provided to what was actually said. Live events must always use domain vocabulary. So as we use automatic speech recognition, we're relying on machines to do that. It's inexcusable to not provide them the names of the players, the names of the hosts, the city where the things, you can just tell ChatGPT to spit that list out for you and provide it to the ASR service. A lot of times we're not even doing this. And we will not get to comprehensive captions until we do, because those are the hardest things to translate. Like player names are impossible because we have players from all over the world. We still need humans. Human transcription is still better than AI. AI is way cheaper. I honestly don't care about cheapness. We also can use human editors when we use AI. Like that information can go to humans and they can do quick correction of proper names and that type of thing. And also we take the live captions and we turn them into the live captions. And when we do that, we have time to actually edit that material. I found in most cases, companies don't bother. They just send in fact, I've seen some cases where the VOD captions are worse than the live captions, and I'm unsure how that's possible. My guess is it goes through a separate pipeline to generate those, and it's not as good as the live one. So luckily, we still need humans. And then when we roll out new technology, and I know that the captioning service companies do this, we need to roll out new technology. We have all this data. We have all these videos and all these captions. We can run all that through simulated live and verify our new technology as it moves forward. All right, so that's the word actually. Speaker differentiation is one of the pain points you all notice. So these are a bunch of words that were spoken by 4 people. That's how the captions appeared. There's actually a disagreement going on in here, but you can't tell who's disagreeing with whom. So a standard way to use speaker differentiation is with the greater than signs. But there's 4 people talking, so you know that's better. You can see that there's some back and forth going on. You can see where thoughts split. They all don't run together. But if you have this, you can actually see that there's a conversation going on and who has which opinion. I mean, and this is just sports, not politics or news or something that, is really important. So we should always have speaker differentiation. I mean, humans and AI are really good at this. It's a really simple problem to say person 1, person 2, or identify this is Anita versus this is Nigel. All right, caption placement. I'm sure you noticed that captions were over top of information you wanted to see. There's some really interesting player side things we can do here. Okay, here's an example. This is the Olympics. It's a time trial. He's coming in to finish. The caption's right over top of the information I want to see about what place he's in and who he's behind. And I could not move those. Here's a U.S. women's basketball game. The caption's right over top of the basket. So what can we do? Well, this is on an iPad. The captions, they're talking about Manchester United and all of their woes this year. why can't I just put my finger on that and drag it over here? Like, that's so obvious, especially on a touch screen. And, on something that doesn't have a touch screen, we could quickly toggle so you could move the caption around. My opinion, and this is probably not a popular opinion, is if I'm going to watch an entire live broadcast, I just want the captions underneath. They will never obscure anything. I know where they are. I can control their size. I can move them around. I lose a little bit of video, but I lose no content. I would love to see some players implement this as an option for people, and I feel very sure that people will use it that need captions. So to summarize, you all have homework. I would like you all to do the live caption challenge. Try to watch a live show you care about for 15 minutes with just captions, and you will get a very deep sense of the user experience. This is a really wide area. I'm still learning a lot. I've been on the technology side. I'm learning more about the user experience and legal side, and so there's a lot to learn here, so I encourage you to learn. Anyone that has caption information, I just want to talk to you. And I think it's funny, make the world a better place, but honestly, this truly makes the world a better place. And it's something, these are the engineering and product leaders in our industry. You're the people in the room when decisions are made. You can push back. You can make suggestions. We are the people that can make this happen. So, thank you.
Any questions?
Not for me.
For Luke about captions.
Hi. How do you define the closed captioning latency and
So how do I define the caption latency? So caption latency is pretty much the moment from when the audio is spoken until when that word appears on the screen. And it's a little fluid because often when the captions appear on the screen, they appear in groups. So I don't know if there's an official way. Like if someone knows, I would love to know. I don't know if there's an official way to measure it, but generally I measure it with a stopwatch. It's like, okay, and it's really ballpark.
you mentioned the AI captions. You mentioned the quality is not the best, and costly is cheaper. How about the timing? Is it faster?
So I don't exactly know. I mean, I think it's in the same ballpark when I've done AI caption integration, it's typically about 6 to 7 seconds. And when you have human captioners, they can, which is amazing to me, they can also do it about 6 to 7 seconds. So it's similar. I mean, honestly, the AI captions, like the transcription is getting really good. It's just, there's a lot of details that need to be taken care of, and it is going to get better. But we do have to measure it. So when is it good enough? We need to know when it's good enough.
A big benefit of the AI captions as well is that you can train your models to also just forward.
Yeah.
And so forth. And that starts helping with the incorrect word issues dramatically and so forth. But either way, whether it's person or AI, part of the issue is just how the data is delivered and that burstiness of it, which creates that latency. So even if it is nearly instantaneous, through the delivery channel, through everything else that you have going on, and just through the standard latency that we run into, it's still a bit of a challenge. But that might be an opportunity where players can actually handle that stuff maybe a little differently and retime that.
I would love it if I could use a player that would
Why can't you shift that forward?
delay the video so it lines up with the caption, because that's a better experience for
Right.
yeah.
But then you need to have something that tells you the data that says, hey, I know I am 4 seconds behind on my subtitles. I'm done now.
I have a question as well.
Yeah.
Are there any tools for positioning and coloring subtitles and things like that for live the same way that they do for professional VOD content? Like shows
Do you
on
mean
Peacock
like 608 or like WebVTT?
Yeah, like WebVTT with styling and positioning so that you can show off the individual speakers.
They're generally delivered
Hard. I
the
know.
same way. Like it's either 608, 708, various different formats. So It's kind of the same issue. I actually don't know if the caption should dictate where they go like that. I think that's sometimes not. Yeah, it can. It has the capability.
There's a technical ability in there to be able to define position and location. And by, at least in the States, you're legally required to enable user controls to adjust how it looks from font, color, size,
Yeah.
Transparency, and so forth. But and that's the problem, is like it's there for in the spec, like, I want it centered on top, I want it bottom left, I want it bottom right. I can move it around, right, to go with the content. But nobody does, because it's work, there's not great tooling, and it's seen as a requirement to appease the FCC instead of to something that's important to users, to be honest.
Yeah.
It's just not, it's like, our whole industry is about saving money and making money, and it leaves, unfortunately, a really important chunk of poor experiences for users.
I would love to see more media companies sued for this, because then it would become a priority. Because there's like a carrot or a stick, and honestly, I think it's only going to be. I would love it if it was always a carrot,
Yeah.
but it's going to have to be a stick.
Yeah, I mean, from my experience, it's always been, what are the requirements? Fine, we met them. Move along.
Well, because they're the
And
lowest,
they're
lowest bar
they're not
possible.
great.
Yeah. Anyway, we can have a longer conversation about this. Yeah.
You were talking how AI subtitles are getting better and better over time. But what about AI subtitles on different languages than English? Because other languages may not have as better speech recognition as English. Have you?
Those are getting quite good too. I just did a project for a company that does work for the UN, and so they have many languages they need to do. And I think they were using Speechmatics primarily, and it has really good multiple language. And their clients were really happy with the quality of the language. It was equivalent to the English. So it's not perfect, but it's really good.
And a back. So I have the pleasure of teaching everybody here about something really boring, something that all these player folks in the room know nothing about, and hopefully you'll learn something. And it's a lot of analogies, so it should be easy enough to follow, but it is a boring topic. Let's get over with. So me, I'm a Luke, or Kickslated. I work at Discord. And I am going to talk to you about congestion control. Basically how the internet works. Because somebody figured it out, everybody uses it, and nobody knows. We're going to talk about analogies. So, because it's too complicated, it's acronym soup. We have a bus. And we have a bus stop. Bus stop is my house in San Francisco, and I want to send video, these little people on the bus, all the way to MonteVIDEO. Think of these as your packets. These are your video frames. So what they're going to do is you're going to stand at the bus stop. I'm going to generate these little frames. They're going to stand there, and they're going to wait for a bus to arrive. And that's their packet. That's their trip to MonteVIDEO. And the bus will arrive, let's say, every 1 millisecond, more or less. The way it actually works under the hood, when we're talking about like Ethernet and Wi-Fi and cable and whatnot, it's a timeshare. So you have some frequency, and you're given 1 millisecond to put some amount of data on it, and then you have to wait. It's somebody else's turn. That's way over abstracting. Like that's how cable works, for example. That's why when there's more people in your neighborhood, your speed is slower, because you're actually giving up more of your time to other people that joined. It's more complicated for other protocols, but you have your chance. So when I generate video, let's say I have these 5 frames I want to send. Some of them can get on the bus. It depends on the size of the bus. They have a weight limit. This is commonly known as the MTU. I'm just going to call it a weight limit. It's the amount of data you're allowed to send in one burst. Again, this is super over abstracted, but hear me out. Again, it depends on the protocol too. Ethernet, for example, you can go up to 9 kilobytes in a single Ethernet frame, even if your packets for IP are much smaller than that. So again, You don't know how big the bus is. You know that some of your packets get, some of your video frames can get in the bus. The others don't make it. The bus goes without them. And what happens to these packets that don't make it? Well, in the really naive case, in the easy case, is they get mauled. They get eaten. They get like it's horrible. These packets get dropped. This is packet loss. When you want to send something, but you just couldn't, like you didn't have a bus space for them, and they don't have anywhere to sleep, and there's vagrants. And so what happens is you have something called loss detection, where before we left, I marked my whole family, put a 1, 2, 3, 4 incrementing, unless you work for Cisco, and so that when they arrived on the other side, I could look and I could see who made it to MonteVIDEO. And sure enough, poor old 4, 5, and 6 didn't make it. We have to send a message back, an ACK, send it all the way back home to say, please make sure they're okay. Like something horrible must have happened. Get them on the next bus. And then the other side will send their cousins or something. So we got the whole happy family now, like, and video plays perfectly, and that's the end. But it's not. Because there's actually an alternate route. So what I just described is how a lot of video engineers think of networks. You send data. If it doesn't make it, you send it again. And you send it again. And you send it again. And like, what could go wrong? So I'm going to tell you what can go wrong. Because that's actually not what happens at all. You have a different route. You have a buffer. You have a bus stop. And you have a bus shelter. They constructed a shelter so you can sleep the night and wait for the next bus. So your packets can actually sit waiting for the next bus to arrive. And they're fine. Unless the shelter gets overcrowded, and then some packets will get lost when your buffer is full. Something's got to give. So the question is, how big should my buffer be? How big should I make this buffer? Should I make it 1 megabyte, 2 megabytes, a terabyte? And the answer is, yeah, you can make it as long as you want. This is a real problem. This is called buffer bloat. This is basically just throwing RAM at the problem and saying, like, hey, I have packet loss. Let's just queue everything. Then no packets will ever be lost. Unfortunately, the queues get very, 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 very long. And it depends on the part of the world you are, which network you're on, which ISP. So anecdotally, this is very common in Brazil and India. You would see round-trip times of like a second, in the seconds range, of just packets that need to be sent, and it just takes forever. So this is buffer bloat. And what happens if we have a very important packet? We have something that needs to be sent. I'm on a video call with somebody, and I need to say, I love you, and I can't wait for 1 second. There can't be that delay. Unfortunately, we have all the other stuff in the queue, and it's useless data. Maybe I was downloading something via torrent or something. I don't know. Like just downloading some useless data. It's in the queue, and my very important packet has to wait. Even worse, the buffer might be full, and my very important packet might get dropped on the fly, on the spot. And just to rub salt in the wound, my retransmission has to wait in line again. So I double the amount of time waiting, just because even retransmissions can't skip the queue. So what if we could skip the queue? We could off with these peasants, whatever. We could get rid of them, and we could skip the queue. And that might seem obvious, right? And this is something you can do with different protocols. Like if you're a UDP-based protocol, you choose which packet to send next. It's something you can do with QUIC. It's something you can kind of do with TCP. So you could decide which packet gets sent next. But the problem is that the internet is a lot of buses. There's a lot of hops. You get to control that first bus station, which is your computer to your router, but every other bus from your router to your ISP, from your ISP to transit, from transit to the CDN to the origin, those are more and more and more and more and more buses. And we don't have any insight into how long those queues are, and we don't have any insight onto how full they are. We don't have any insight onto anything, really. And this is the problem with the internet, is it's a black box. You send packets in, and something happens. In order to get a very important packet through, we need to try to do anything we can to control the stuff in the middle. And that is congestion control. So how do we fix it? So number one, we need to stop these network queues. We need to, and we can do that in two ways. We can detect that there's queuing somehow, and then we can drain the queue somehow. There's no magic packet we can send that says, please nuke everything on the queue, and there's no packet that tells us that the queue is this big, so we have to get smart about it. The most obvious way is in this ACK, we know that, oh hey, some packets were dropped. We can use that to assume a queue somewhere must be full. That must be why the packets were dropped, right? A queue must be full somewhere. And we can use that as a sign to say there's probably too much data in the pipe, and we need to stop sending. We need to let stuff drain. And this is how TCP works, more or less. So TCP Reno, which is used on Windows, the bitrate will increase very exponentially at first. It's called slow start, even though it's really fast. And then when there's packet loss, the bitrate drops by 40%. And then it increases, drops by 40%. Increases, 40%. It creates a sawtooth pattern. On Linux, it's TCP cubic. It's very similar. They just got smart and made it cubic instead of linear, but the exact same thing. But the problem with these is actually kind of subtle. And the reason why TCP is not good for real-time streaming is this slide. Is because if we graph the amount of time it takes for each packet, if we look at how much time it takes for the latency for each packet, it starts really small. It's like speed of light, basically. And then as queues build and our wait time starts increasing, each packet takes longer and longer to send, until eventually we hit some cliff and we start dropping packets. That cliff could be 1 second long. It depends on your network. It could be 100 milliseconds long. It could be whatever. We don't know what it's going to take until some router somewhere starts dropping stuff on the floor. And that's when we back off. That's when packet loss happens, and now we stop sending data, and we slowly drain the queue, and then repeat the cycle. So this is what happens with a lot of legacy TCP algorithms, and it's why latency is usually pretty high. So yeah, buffers grow until they're full, and then we can shrink a little bit, and then we repeat. And this sucks. It sucks. You can't do live streaming using, if you've used RTMP, for example, from a Windows machine, you'll know that sometimes your latency just goes up and up and up and up and up until it's like in the 5-second range before it starts draining. Because this causes the maximum latency possible. We basically will fill up any queues on the network until they are completely full, the maximum latency, before anything starts to slow down. It also causes an inconsistent bit rate. We cause plus or minus 40%. We actually need a much bigger overhead now. Our ABR algorithm has to be a lot more conservative because it's worried about the sawtooth. So it's pretty bad. So yeah, how do we fix it? This slide again. So we can actually use the previous acknowledgement, the symbol that says like the other side when it receives the packets. Instead of telling me which packets were lost, tell me when they were received. Just give me a timestamp. I know there's numbers here, but basically the other side just sends a timestamp. And what we could do with that is we can actually just plot it. If you tell me when a packet was received instead of when it was lost, I can graph this and I can see the latency going up. I can see that there's a queue somewhere on the network, somewhere on some router somewhere is backing up. And I can aggressively back off and avoid the higher latency altogether. I can make it so that my video call is uninterrupted. Maybe there's a tiny hiccup, but I don't have a big buffering spinner when I just oversaturate it. So this is what BBR does. This is effectively run by every cloud provider on the internet. So like 99% of TCP uses this now. It uses the TCP acknowledgement to measure the round trip time. So it just built. You don't need a protocol change. Google was smart enough to figure out how to make this work for TCP. The problem is that the ACKs are delayed. So it might wait. A receiver might wait like 20 milliseconds before sending you there's an ACK, and they're also batched. So you might have hundreds of packets in one ACK. So you don't really know when each packet was received. You get really fuzzy math. It's really fuzzy, hand-wavy stuff. But when I enabled this at Twitch, this caused 11% more minutes watched in Brazil. So just turning on, in Linux, you just enable a flag, 11% more video was served, which is crazy for something that simple. Quick also supports BBR. Quick actually just borrows TCP's congestion control. It is more like TCP than it is WebRTC. It also can use the Axe. It actually fixes one issue. In the acknowledgements, it tells you the delay. So you can now get more granular feedback. You can actually tell when a packet was received, when an ACK was received at least. Unfortunately, there's still batching, so you still have to guess. They're still clustered together. Although there is an extension to change that frequency. So you could tell the other side, please send an ACK every 5 milliseconds if you want a really noisy protocol. And you can go a step further, and this is what WebRTC does. Again, Google did this, transport-wide CC. Effectively, a WebRTC client will, every 100 milliseconds, will report the timestamp of every packet it's received. A big bulk, and just say, this is when I received every packet. You plot all the data points, and you figure out, oh, latency's going up, back off aggressively. So this is how WebRTC can do really low latency. It's called Google Congestion Control. It's the worst acronym ever, because it's GCC. But it's really good, and this is something that honestly needs to be added to Quick if we want to like really reach WebRTC parity. There is an extension out there. Google's like put forth, published it, but nobody's actively pursuing it right now. And the future, because you have to talk about the future here. It's not AI, not in this space, not yet. Something called L4S, where effectively the routers get a new packet type where they get to tell the other side, or you get to tell you if you send too much, they say back off, like buffers are increasing or packets are being lost. You don't need to figure out with math and logic and algebra or whatever if packets are being dropped or about to be dropped. The router will just tell you that you need to slow down. This is being rolled out. This is an IETF. It's being rolled out, but it's on a per network basis. So it depends on ISPs implementing it, which means it will probably never see the light of day. Because there's a lot of features like that, like multicast and whatnot. We'll see. But this is a silver bullet. This effectively even lowers the feedback cycle even shorter. So yep, we managed to detect queuing. And we can drain those queues to keep latency low, and we can avoid packet loss, in fact, altogether. So my rant here is a lot of people in the video industry report packet loss as one of their primary metrics. You've already messed up if you get packet loss to some degree. There is random packet loss, but what's really interesting about this buffer bloat is if you get a packet loss because the buffer is full, you need to send less data. And if you get buffer bloat because, if you get a packet loss from random, you need to actually send more data. You need to send it again. What we can do is we can actually look at this graph. Now that we have the delays, we can figure out there was packet loss at the highest delay. We know that was because it's congestion. If we had a packet loss down at the bottom, we know it was just random, like some interference pattern somewhere. You know, somebody turned on their Wi-Fi router at the same time or something, I don't know. So we can actually classify the type of packet loss. It's not random, it's not just congestion. There's actually 2 different types. And that's it, actual end. There is a bonus rant, but I'll skip that. Any questions? Okay, I'll do the bonus rant. Just kidding, I will not do the bonus rant. The bonus rant is actually, again, around packet loss, is when people over-fixate on packet loss, and you use network simulation. You turn on a network simulator, and you turn on 10% network packet loss or something, and you say, my protocol is amazing. The reality is the internet doesn't work like that. So what I want to really like rant about is packet loss as a consequence. You've already caused queues to build up so far that packet loss happens. And if you send more data, you'll cause more packet loss. So you have a lot of cases like this is Opus 1.5, where they said, and yes, our protocol works great with 90% packet loss. They used ML and FEC, which is sending redundant copies of the same data. And they said it works under 90% packet loss. But if you really think about it, 90% packet loss means you're sending 10 times too much data. And their solution they claim works great is you send 20 times more data than the network can handle. And suddenly everything's fixed. So this works in a lab. This is when you actually simulate with packet loss. You turn on a network link conditioner. You can get results like this. But the reality is, even an algorithm like TCP Reno, this goes to 0 if your random packet loss is 10% or something. Like, random packet loss actually doesn't really exist. Otherwise, TCP wouldn't work. So when people simulate random loss and tell me all about their new UDP-based protocol or the new ABR algorithm or their new like FEC thing in the video space, you gotta run it into production. Unfortunately, you gotta actually get numbers because networks are a black box, and trying to simulate them is impossible. I'm just gonna say it's impossible. And so many people run into this mistake where they just, yeah. It's unfortunate because a lot of academia wants to do stuff on congestion control, but it's just out of reach because you need the data. And that's why Google primarily iterates on it and innovates on it, because they have the data. And that's it. That's actually it. I have a tablet at home, a drawing tablet, and I use an open source painting program. So I paint the slides. This took maybe like 2 days to draw.
These were your actual handwriting.
Yeah, it's pretty bad, so it takes a long time for me to draw these, because I have to hit erase a lot.
Great presentation, thank you very much. A couple of questions. One is, can you remind me if the packet actually makes it over, is the content guaranteed, or is there a chance that some bits will get flipped along the way?
So it depends on the protocol. For example, IP has a very basic checksum. So there's checksum at the IP level. There's usually checksums at the lower levels, like at the Ethernet level or the Wi-Fi level. And my rant about FEC, I forgot about this. Again, a lot of people in the video industry say we send redundant copies. Wi-Fi does that, and cellular does that. All these protocols already have their own checksums and retransmissions and FEC, because they know the underlying loss properties, and they can choose based on the network how much recovery is needed. And then us as video engineers, we just kind of say, every network needs 20% more bits sent, and then it recovers from packet loss. And that's just one of my frustrating rants, is the actual protocols a lot of times will handle bit flips and will handle these things, and it will get dropped silently without you realizing it.
Okay, thank you. And my second question is, in past I had good experience measuring my level in the output buffer to throttle the encoder, but perhaps that's not quite bulletproof, right? It's like better to be looking at the receiving end, because I might be just the different queues might be just feeding each other, right?
Yeah, so your output buffer is gated by this congestion control I'm talking about. So the TCP module in the kernel is the one limiting the send rate and causing that buffer to grow. But how it decides that there's queuing is sometimes not great, if that makes sense. And it's already too late. If the congestion shows up in your send buffer, that means it's already on the network, more than likely. And that's why, again, with RTMP, looking at the send buffer is usually not enough. It's not like a magic solution to make RTMP low latency, like WebRTC. You need to go WebRTC levels where you control every packet you send before it reaches the send buffer. Because once it's in the TCP send buffer, you can't take it out. That's like the fundamental problem with TCP. That's why Quick actually solves this issue, because Quick lets you put it in separate send buffers, which the library can choose when to send them.
And perhaps the last question, if I may, what about QoS? Can't you probe the network and provide some control over?
There are QoS flags you can set on packets. This is another thing that is specified, but networks don't really obey. You can put a bit on your packet saying this is high priority, this is a VIP packet. It doesn't work, because everybody would turn it on. That's the thing. Like, everybody would say my packet is highest priority, so it's not. And actually, a lot of the time, you end up hurting yourself by using UDP, because other people try to game the system by using UDP, and ISPs now throttle UDP across the board. So unfortunately, like, trying to win by saying your packet's more important just doesn't work.
I've got a question. So how does congestion control within mobile networks affect what you're doing?
So I don't know too much about mobile networks. This is something where I'm kind of, again, standing on the shoulders of others with congestion control, because I haven't actually really looked into what they do too much. But it's a similar concept. It's you try to avoid buffer bloat. Buffer bloat is pretty bad on a lot of cellular networks. Anecdotally, T-Mobile's pretty bad, I think. There's a few of them. Like, when we look at stats, when I was at Twitch, we would collect an ISP worst offenders list. And Discord does something similar. Apparently, Google Fiber is pretty bad, like in Denver or something. One location is really bad. So we look at a lot of the networks, and we just run experiments. You run experiments, you see if it helps, because it's really hard to know why a mobile network is poor.